How can you solve a linear program with the graphical method? In this video, I will show you how to do this such that by the end of this video, you will know how to do this yourself. With this method, you can solve linear programs with exactly two variables. For example, this linear program that you see here. Its variables are called x1 and x2. They can have arbitrary names. They can also be called differently. In my example, they're called x1 and x2. The first thing you need is a coordinate system for your variables. So for my example linear program, I want to use this axis system here where this axis here corresponds to x1 and this axis here corresponds to x2. Now every point in this coordinate system corresponds to one potential solution. For example, this point here to 1, so x1 is 2, x2 is 1. Corresponds to one potential solution, and also this point here, 6, 4, where x1 is 6 and x2 is 4, corresponds to one potential solution. Now, if you check, you will see that the point to 1 actually satisfies every single constraint of our linear program, so there's one feasible solution, whereas the red point does not, because, for example, it violates this first constraint here. The next step is to draw the points that are feasible solutions for our linear program. These feasible solutions are exactly those points that satisfy every single one of our constraints. So let's look at our constraints. Let's start with the first one, this one here. And it turns out that the points that satisfy these constraints are exactly the point here underneath this line here. How did I figure this out? Well, one way to figure this out is to use a computer program like or some service like Geogebra or WolframAlpha. If you cannot use that, for example, if you are in an exam and you have to solve this by hand, you can do the following. First, you draw this line here, which is the line of all the points where 2x1 plus 3x2 is not just less or equal than 18, but it actually equals to 18. Okay, how do you find this line now? Well, one simple way of doing that is to find 2 points on this line and then connect them. So for example, you can take the point 0, 6. This point satisfies this equality. And you can take the point 9, 0 that also satisfies this equality and connect them with the line. By the way, in order to find these points, you can take any 2 points on the line. However, these points here where either x1 is 0 or x2 is 0, they're convenient for you because if x1 is 0, then it's easy to figure out what x2 has to be, because then 2 times x1 equals to 0. And therefore, if you want to know that here you have to put 6 for x2, you just need to solve 3x2 equals to 18, and then clearly x2 has to be 6. Now, you know this line here. Then the points that satisfy this inequality here, from all you know, they're either above the line or underneath the line. In principle, both is possible. So how do you figure out which of the two cases applies? Well, what you do is you just take an arbitrary point that is not on this line here. So for example, this point here, 0, 0, and you check whether it satisfies your inequality here. And in this case, it does, because 2 times 0 plus 3 times 0 is 0, and this is clearly less or equal than 18. So therefore, you know that this point satisfies your inequality, and therefore you know that all the points that satisfy the inequality are all the points here, right underneath your line here. How about the other constraints? Well, for the second constraint here, you have pretty much the same thing. All the points that satisfy it are all the points in this region here, underneath this line here. And for the constraint x1 greater or equal than 1, it's almost the same thing. The only difference is that, or say specialty, is that this line here is now a vertical line. So in particular, you're not going to find a point on this line where x1 equals 0. It's like a point here. However, it's actually fairly easy to find this line, because if x1 is 1, then you get exactly the points in this line here. And also it's actually super easy to figure out on which side of this line you have your feasible points, because the constraint says that x1 has to be greater or equal than 1, And these are clearly all the points here on the line where, for example, here x1 is 1, 2, 3, 4, and so on. And similarly, for the last constraint, this is the set of feasible points. So, therefore, all the points that satisfy the first constraints are here. All the points that satisfy the second constraint are underneath this line here. Third constraint, fourth constraint. So therefore, all the points that satisfy every single one of these constraints are exactly the points here in the middle, which are these points here. Good. So now we know all the feasible points of our linear program. However, we do not just want to find a feasible point, but we want to find an optimal point. And in order to find an optimal point, we have to talk about the objective function. Our objective function is to maximize x1 plus x2. And now let's draw this objective function. More precisely, what I draw is I draw all points where this objective has the same value. For example, I draw this line here that contains all the points where my objective function has a value of 3. Now what happens is that if I move this line up to here, then again I get points, all points there where the objective function has the same value, in this case the value of 4. If I move it even further up, again I get lots of points where the objective function has the same value, which is in this case the value of 5. And as you probably notice, the further up we move this line, the better becomes our objective function. Yeah, remember that we want to maximize x1 plus x2. And typically people indicate this with an arrow like this one here when they draw the objective function in such a picture. So now if you want to find a point that is optimal for our linear program, what we do is we take this objective function and we move it up as far as we can, such that it just still intersects one point from our feasible region. And in this case, this is this point here, the point 3, 4, and this point is optimal because it is a feasible point. And if we moved our objective function a little bit further up, then it would no longer intersect any point from our feasible region. So therefore, this point here is optimal. And the value of our objective function at this point is 7. Excellent. We found the optimal solution for our linear program with the graphical method. Let me point out that there are some linear programs for which we cannot find an optimal solution, simply because they do not have one. Let me show you why. In this linear program here, the feasible region extends arbitrarily far to the top and arbitrarily far to the right. So therefore, if you take this objective function and move it further and further up, you can move it arbitrarily far up. You will find better and better points in the feasible region. So therefore, there is not a single point that is optimal, meaning that there is no other feasible point that is better. But instead, the correct answer here is that the linear program is unbounded. Another thing that can happen is that the feasible region is the one that you see here, meaning that it is empty. And this is the case because we have the constraint x1 plus x2 less or equal to 1. But on the other hand, we have the constraint that already x2 has to be greater or equal than 2. And these two constraints contradict each other. So therefore, there is not a single feasible point. So in particular, there is no optimal point. And in this case, we say the linear program is infeasible. So now you know how to solve a linear program with the graphical method.